Hello everyone, I'm Norman Wildberger. We're here at the University of New South Wales, and this is a course on differential geometry. Today we're going to look at a very important sort of elementary issue of the role of the differential calculus for curves. So this particular lecture is probably going to be of broader interest. It'll probably appeal to anyone who's studying calculus or teaching calculus, because I'm basically going to present an alternative kind of view to calculus, different from the one that one finds in the standard texts. This is a powerful alternative that has a very strong algebraic focus and was in fact initiated not recently, but quite a long time ago. It was really an outgrowth of the work of Euler and Lagrange. So Euler and Lagrange, well, they're both pioneering figures, of course, in mathematics generally, the towering figures of 18th century mathematics. First Euler, and then he passed on the torch to Lagrange. And they had a rather algebraic approach to analysis that was, I suppose, enunciated very clearly by an important work of Lagrange. And the work is called Théorie des fonctions analytiques, or Theory of Analytic Functions. So that was written in 1797. And the subtitle is very interesting. Here's the English translation of the subtitle, it's very long. So, Theory of Analytic Functions containing the principles of the differential calculus, disengaged from all considerations of infinitesimals, vanishing limits, or fluxions, and reduced to the algebraic analysis of finite quantities. So that was the subtitle of Lagrange's important 1797 work, Theory of Analytic Functions. So in that work, he embraces Euler's thinking and lays out an approach to calculus, which we're going to follow today. Okay, and it'll probably be novel to most of you, and you may easily wonder, why are we not learning calculus this way, rather than the more complicated way that we generally learn calculus today? It's a very good question, and it's an important question that educators really ought to give some serious thought to. All right, so let me start by reviewing the standard approach to calculus, and let me do it in the context of a particular polynomial. So let's take the polynomial, say p of x equals 8 minus 5x plus 4x cubed minus x to the fourth. Okay, that's a quartic polynomial. Oops. That looks something like this. Okay, maybe here's 20 and minus 20 and 1, 2, 3, 4, minus 1, minus 2, minus 3, and so on. Okay, it looks a little bit like this. Okay, all right, so that's just a random polynomial. And suppose we choose a point on it, say point minus 1. Then what are we doing when we do the differential calculus? Well, the first object of interest is the tangent line to the curve at that point. So we're looking for a line passing through that point, which is in some sense a good approximation to the function. And we all know how to do that. What we do is we choose a nearby point, and we draw a secant line between the point in question and the nearby point. And we then let the nearby point approach the given point, and then that secant line will approach the tangent. Okay, so once we have that tangent, what's of interest to the tangent, or about the tangent, is its slope. So we say S is the slope of this tangent line. And that's usually in terms of a ratio of changes of y and changes of x, but we have to sort of take in a limiting way. All right, so we get a number. Okay, we get a number. So in this case, this thing here, well, maybe a change of 2, a change of 10 or something like that. So maybe there's a slope of 5 or something like that. All right, so what we do then is we plot that value. Okay, so we define p prime of x to be equal to the slope of the tangent line at x. And that gives us, okay, another value here. And then we can do the same thing for various points on the curve, and we get the derivative. Okay, so the derivative will be what? Well, maybe it goes 0 here, a little bit negative. Through the 0 there, there'll be a 0 here. Okay. So the derivative is something like this. Okay. And that's then so the basic object of differential calculus is usually presented to go from the function p of x to its derivative p prime of x. And we also might call this, say, just dp of x, d standing for differentiation operator. Okay, now in practice, students learn what this actually is. In this case, the derivative is minus 5 plus 12x squared minus 4x cubed. And that's a consequence of a couple of different formulas. One of them is a very fundamental formula that the derivative of x to the n is n to the x to the n minus 1. That's a fundamental fact. And then another kind of fundamental fact is that if you have two polynomials, the derivative acts linearly. So that we can break up a derivative like this into a sum of lots of little derivatives, and then we just use this formula over and over again, and we can write down the derivative. Okay, and then we have the notion of the second derivative. So then the second derivative of p is by definition d of p, and we can keep going with higher derivatives. Okay, so this is fine. There are some requirements here that are a little bit subtle. One is this limiting quantity, this limiting idea. Another is there's an underlying assumption of sort of real numbers that we assume is underlying this limiting business. In the 18th century, mathematicians previously had approached these limits in rather dodgy ways using so-called infinitesimals. And a bishop, Irish bishop Berkeley, wrote a scathing denunciation of the techniques that were being thrown around at the beginning of the 18th century. And this motivated mathematicians to start saying, well, what are we actually doing here? Can we be a little bit more precise about this limiting process? And it was partly in response to that Lagrange and Euler would have tried to frame this discussion in a different way. All right, so what I want to do is I want to give you a completely alternate or different approach to the differential calculus now. And I'll stick with this same example so we can sort of see what happens. Okay, so what I'm going to outline now is really the approach of Lagrange. Which, rather remarkably, has almost completely dropped off the radar screen here at the beginning of this new millennium. Okay, so what is Lagrange's approach? Lagrange says, all right, let's start with this polynomial p. And let's consider p of x plus y. Okay, he may not say it exactly. This is my reformulation of Lagrange's idea, but it's basically Lagrange's idea. All right, so we're going to look at p of x plus y. We're going to introduce another variable. And we're going to just write this out. So this is 8 minus 5x plus y plus 4x plus y cubed minus x plus y to the fourth. And we're going to expand this out because we know the binomial theorem. So this is 8 minus 5x minus 5y plus 4 times x cubed plus 3x squared y plus 3xy squared plus y cubed for that term there. And then minus x plus y to the fourth would be x to the fourth plus 4x to the fourth y plus 6x squared y squared plus 4xy cubed plus y to the fourth. So correct me if I make a mistake there. Okay, and now what we can do is we can rewrite this by sort of separating the x's and y's. So we can write this as another polynomial in x with coefficients in y. So we get 8 minus 5y plus 4y cubed minus y to the fourth. That's sort of the constant term. So I've done this one, this one, this one, and this one. And then there'll be the terms linear in x. So that will be plus minus 5 plus 12y squared minus 4y cubed times x. So now I've picked up minus 5x, 12y squared x, and minus 4y cubed x. Oh, there's a minus sign here, yeah. So the minus sign, so that should be a minus sign, that's fine. Okay, and then the x squared terms. So then there'll be plus 12y minus 6y squared times x squared. And then there'll be 4 minus 4y times x cubed. And a single minus x to the fourth left over. All right, now I'm going to rewrite that formula slightly. And now what I'm going to do is I'm going to replace x with x minus y in this formula. All right, so if I replace x with x minus y, then I'll just have x here. So p of x equals right here. So I'm only replacing the x's. So I still have 8 minus 5y plus 4y cubed minus y to the fourth plus minus 5 plus 12y squared minus 4y cubed times x minus y plus 12y minus 6y squared times x minus y squared plus 4 minus 4y x minus y cubed minus x minus y to the fourth. So this is an identity. You can think of it as a way of rewriting the original polynomial. The original polynomial is now also equal to this. So if we expanded this all out again, we would just get the original polynomial, which was, well, actually we can read it from here. 8 minus 5x plus 4x cubed minus x to the fourth. All right, so now it's perhaps more convenient or more usual to replace y, which is up till now just another abstract variable, with a number. Okay, so let's replace y with a number. We could have done this at the beginning, but okay. So then we would get, well, let me write it. P of x equals 8 minus 5r. The number will be r. 5r plus 4r cubed minus r to the fourth plus minus 5 plus 12r squared minus 4r cubed times x minus r. And do I have room in here? Plus 12r minus 6r squared times x minus r squared plus 4 minus 4r times x minus 4r to the cubed minus x minus r to the fourth. So I've just taken this thing and replaced y with r. I'm thinking now of r as a number. Okay, so what does this do for us? Well, this identifies certain polynomials are arising here that are occurring in the coefficients of these various increasing powers of x minus r. Okay, and what are those polynomials that are appearing? Well, let me write it without writing them all down. Let me write this as d0 of p of r plus d1 of p of r times x minus r plus d2 p of r x minus r squared plus d3 p of r x minus r cubed plus d4 p of r x minus r to the fourth. So what are these polynomials? Well, we can see that d0 of p is just really exactly the same as the original polynomial p. Polynomial was 8 minus 5x plus 4x cubed minus x to the fourth. That's exactly the same thing there. And this next one, what we're calling d sub 1 of p, is what's usually called the derivative. That's the derivative. The derivative of this is minus 5 plus 12x squared minus 4x to the cubed. So that's the, like p prime, it's the derivative. We also have these other ones. So d sub 2 of p is not exactly a second derivative. If you took the second derivative, it would take the derivative of this, you would get 24y minus 12y squared. Here we're only getting half of that. So it's what we might say the second derivative, if you know what that is, of p divided by 2. And then the third p is the third derivative of p over 3 factorial, and so on. Okay, I like to call these functions subderivatives. Subderivatives of p. Yes? Yes, that's the Taylor expansion of the polynomial, which is something that usually comes quite a little ways into a calculus course after you've done a whole bunch of other things. So what Lagrange is saying is that we can go directly right to what we call the Taylor expansion. Basically, Lagrange knew this. We can do it directly using just high school algebra. And once we look at things that way, then not only do we get the first derivative popping up for free, but up to this a little bit normalization, we get all the derivatives listed right there for us. Okay, in fact, there's a nice way of getting these all these coefficients. So what we're really doing is just using the binomial theorem. So if we look at Pascal's array, which I'll write like this. So 1, and then 1, 1, and then 1, 2, 1, and 1, 3, 3, 1, and 1, 4, 6, 4, 1, and so on. 1, 5, 10, 10, 5, 1, and so on. Then what we're doing is we're just multiplying these diagonals by the appropriate coefficients in our original polynomial, 8, minus 5, 0, 4, and minus 1. So I'll put maybe a 8 here, and then minus 5, and then the x squared coefficient is 0, and then there's a 4, and then there's a minus 1. All right, so if we multiply each of these sort of diagonals in this direction by these numbers, we get the array 8, minus 5, minus 5. To multiply that by all by 0. 1, 3, 3, 1 gets multiplied by 4. So 4, 12, 12, 4. No, oh yeah, that's right. And then the 1, 4, 6, 4, 1 gets multiplied by minus 1. So that's minus 1, minus 4, minus 6, minus 4, minus 1. And then that array there, we have immediately all the subderivatives ready for our reading off. There's 8 minus 5, 0, 4, minus 1. That's the original one. There is the first derivative. There is the second subderivative, 12y in the right columns, and then 4 minus 4y, and then minus 1 there. So if you didn't feel like doing all this calculation that I originally did, once you've done it once or twice, you realize all what you really need to do is you take this Pascal's array, multiply the columns by the coefficients of the matrix, and boom, all the information is right there, right in front of you. All right, so that's good. So what can we do with that? Well, one pleasant thing to do is to follow Lagrange and say, all right, suppose that we have two polynomials. So we have one polynomial p, which we'll write as d0 of p of r, okay, everything's of r, plus d1 of p of r times x minus r, plus d2 p of r times x minus r squared, and so on. And then we'll have another polynomial, let's call it q. So we'll have a similar expansion, d0 of q of r plus d1 q of r x minus r plus d2 q of r x minus r squared, and so on. Then if we multiply these two polynomials, p times q will then be, well, the zero term will be d0 of p times d0 of q, okay, at r. And then the coefficient of x minus r will be d0 of p times d1 of q plus d0 of q times d1 of p, all of that at r times x minus r. And then the next one will be the coefficients of x minus r squared will be, there'll be a d0 of p times this d2q plus a d1p times a d1q, and also a d2p times a d0q. Okay, all of that actually evaluated at r times x minus r squared, and we can easily see what the pattern is. Now, of course, that has to also be equal to the corresponding series for p times q. So that has to be d0 of p times q at r plus d1 of p times q of r at x minus r plus d2 of p times q x minus r squared, and so on. Okay, so what can we conclude? Well, we conclude it's obvious that d0 of pq is equal to d0 of p times d0 of q, because that's just p times q. But what's maybe not so obvious is that we now know that the derivative of p times q is, well, d0 of p is just p. So p times d1 of q plus q times d1 of p. A familiar product rule for derivatives. But we can read off more. We can read off that the second derivative of the product is p times the second derivative of q plus the derivative of p times the derivative of q plus q times the second derivative of p. We could just as easily write down corresponding formulas for the third derivative of a product or the fourth derivative of a product and so on. Okay, so that's good. But we're interested in geometry here. For us, what we're interested in differential geometry is to study a curve or a surface near a point. Okay, we're interested in the shape of things near points. So we're interested in, how do you describe the shape of that curve near that point? Or how do you describe the shape of this surface near that point? So for this, this Lagrange kind of expansion is very useful for the following reason. So we're going to imagine, well, we'll just take, this is the basic formula there. And what we can do is we can truncate that. Okay? So to find approximations to the curve p of x at the point R, we truncate our all-important formula star. What that means is we're going to consider a number of approximations, and we're going to give them names. So the first one, this will all be at the point R. The first one, or the 0th one, we'll put a 0 up here, of p is just, by definition, d0 of p, which is just at R, which is just p of R. Okay, t sub r1 of p will be what we get when we take, I might just write, okay, d0 of p of r plus d1 p of r times x minus r, and d2p is the sum of the first three terms, all quantities up to degree 2. And in general, we take t r k of p is the sum of all terms in star up to and including degree k in x minus r. And we'll call this the kth tangent, to p at r. Okay, let's go back to our example. And all right, so for our original curve, which was p of x equals 8 minus 5x plus 4x cubed minus x to the fourth. For that example, a star looked like, well, I'll write it again. So p of x equals 8 minus 5r plus 4r cubed minus r to the fourth plus minus 5 plus 12r squared minus 4r cubed x minus r plus 4 minus 4r times x minus r cubed. And well, there was a square term here. Let me squeeze it in here. 12r minus 6r squared times x minus r squared plus 4 minus 4r times alpha minus x minus r cubed and minus x minus r to the fourth. All right, so what do these various tangents to p at r look like? So the zeroth tangent at some point r is just this. It's just a number. That's just p of r. It's just a number. The first tangent is, well, we have to take the sum of the first two terms. So we have to take 8 minus 5r plus 4r cubed minus r to the fourth plus minus 5 plus 12r squared minus 4r cubed times x minus r. That's an equation that's linear in x. Actually, we can, if we want to, sort of simplify it, because we could now expand this out if we wanted to. And we would get 8 minus 8r cubed plus 3r to the fourth plus minus 5 minus 4r cubed plus 12r squared times x. That's then an equation of a line whose coefficients depend on r. Okay, what about d sub r2? The second tangent to the curve. Well, we have to take the sum of the first terms up to degree 2, including degree 2. So we have to take 8 minus 5r plus 4r cubed minus r to the fourth plus minus 5 plus 12r squared minus 4r cubed times x minus r plus 12r minus 6r squared times x minus r squared. That's going to be a quadratic. And you can expand that out too if you want to. I'm going to just tell you what it is. Okay, it turns out to be 8 plus 4r cubed minus 3r to the fourth plus minus 5 minus 12r squared plus 8r cubed times x plus 12r minus 6r squared times x squared. And we could keep going. If we went to the next one, since, well, we would get a cubic. Maybe I'll tell you what that is. I'll write down the simplified form. So the third one is 8 plus r to the fourth minus 5 plus 4r cubed times x plus 6r squared x squared plus 4 minus 4r times x cubed. And the fourth one, well, that would just be p itself. That would just be P of x, because that would be the everything. So what we have now is a hierarchy of approximations to the original curve. The hierarchy obtained simply by truncating this Taylor or Taylor-Lagrange polynomial, just truncating it up to whatever number of degree terms we want. If we go just one term, we're just getting a constant function, which is the value of the polynomial at the point r. If we go to the first terms, we get an equation of a line, and that's the tangent line. Here it is. That's the tangent line to the polynomial p at the point r. And the second degree one is the tangent conic. We'll give it this name. We'll call it the tangent conic to p at r. And this third one, we'll call it, well, we can call it the 3 tangent, or we'll call it the tangent cubic to p at r. Okay, so this is very, very important for differential geometry, right? We're interested in curves and surfaces. We're interested in understanding what things look like near a point. Here we have a succession of increasingly sophisticated approximations to a curve at a given point. Starting with the function's value, then going to the tangent plane, and then introducing this perhaps new idea to you. It's almost surely new to most of us. The idea of the tangent conic to the curve at a point. And then one step further, tangent cubic, and we can keep going if we want, getting better and better approximations to a curve at a point. Let's have a look to see what it actually looks like for our running example. So, okay. Okay, so here's this kind of thing can be done, of course, very pleasantly with GeoGebra. All right, so maybe here's 20 minus 20, 1, 2, 3, 4, minus 1, minus 2, minus 3. All right, so the curve itself, so there is p of x. I remind you that was 8 minus 5x plus 4x cubed minus x to the fourth. That fourth degree polynomial. Let's choose the point r equals minus 1. Just as an example. So r equals minus 1. Okay, so up here at minus 1, the function's value is 8. So the value actually is 8. Okay, so the zeroth, at minus 1, the zeroth approximation to the polynomial is just the number 8, represented by just that dot, or if you like, you can think of it as a constant function if you like. Okay, then at the tangent line, if we take the equation for the tangent line and plug in r equals minus 1, we get this tangent line, which looks like this. All right, so that's t, that's the tangent at minus 1, the first tangent of p. That is then, has equation 19 plus 11x. That's the equation of the line. There it is there. The tangent conic. Okay, here's what the tangent conic looks like. Okay, it approximates it better. Okay, it is, so here's the tangent conic, which is t at minus 1 second degree of p, and that is equal to, write it in this color so you can see, 1 minus 25x minus 18x squared. That's the tangent conic. That's the tangent line. There's also a tangent cubic, which is over here. If I plug in r equals minus 1 to that, I'm going to get an equation of a cubic. What's that going to be? It will have the form something like that. So that's the tangent cubic of p, which is 9 minus x plus 16x squared plus 8x cubed. All right, so here's a little problem for you. Problem: calculate and graph the tangent curves 2p at the point r equals 3. So that point over there. Okay, so why is this interesting? Well, admittedly, there was a bit of work. There was a bit of algebra. Right? We had to do some fiddling around with polynomials. But in some sense, that's completely trivial kind of arithmetic. These days, a computer algebra system does that stuff just like your calculator does, multiplies big numbers. Simplifying polynomials, expanding them out, grouping terms. These are all ultimately almost trivial operations these days with a calculator, with a computer algebra system. Like Maple, or Mathematica, or MATLAB, or even GeoGebra will do some of that for us. All right? So in previous generations would have found some of this onerous, but these days you can get your computer to do this almost instantaneously. You can generate these kinds of pictures very, very easily. Okay? The point is, we're not using limits. We've avoided any discussion of limits. We've avoided any prior understanding of real numbers. Everything's just been over the rational numbers. And it's all really been with high school algebra. And what have we done? We've established, well, the derivative, essentially the higher derivatives, and it's been easier for us to get at these curves. In the classical setup, to get the tangent line, first you have to compute the derivative, and then you have to do some analytic geometry to get the tangent line. Here the tangent line is just what you get by truncating the Taylor expansion, Lagrange Taylor expansion. The tangent conic is just what you get by truncating. The crucial operation is truncation. Okay, but there are some other very important consequences. And we'll talk a little bit about these in further lectures. So one important consequence is that everything is algebraic. Basically, we're only using addition, multiplication, subtraction, and division. So it really works over a general field. So the discussion holds over a general field. In particular, it holds over a finite field. Okay? So we are now in the position of being able to do calculus over a finite field. And I'll show you some examples of that perhaps next time. Even looking at this over a finite field makes perfectly good sense. Secondly, this generalizes to more dimensions more readily than the usual business. So it generalizes more smoothly to not just one-dimensional calculus, but two-dimensional calculus, to calculus of several variables. So calculus of several variables is something that you usually only do in a second university course in calculus. But we'll see that this approach means that you can basically almost immediately start thinking about functions of more than one variable. Another is that the importance of the tangent conic, I think, comes out. Okay? So these tangent conics are remarkable things. Obviously, if you're interested in approximating a curve, you shouldn't just restrict yourself to the tangent line. Yes, the tangent line is a useful first approximation. But for finer, more refined work, you may very well prefer working with this tangent conic, which approximates the curve better than the tangent line does. That's going to be a very, very important idea for us in differential geometry, because in some sense, a lot of differential geometry is really built on the idea that we should approximate curves and surfaces quadratically. Not linearly, but quadratically. How we do that and with the consequences of that, that's really a core issue in differential geometry. And next time I'm going to show you what I consider the most beautiful theorem in calculus, okay, which is a direct consequence of looking at this idea of tangent conics. And we'll actually, it's just an absolutely remarkable thing that was first observed by Etienne Guise. So we'll look at that in the context of osculating curves. So lots of interesting potential for this. Students of calculus, give it some thought. Okay, and a purely algebraic approach, going back to the masters, Euler and Lagrange. See you tomorrow.